Section 4.4 is titled The Fundamental Theorem of Calculus. All right, so like I said before, what we're going to do is we're going to find a way to find that exact area under the curve and how it relates to antiderivatives that we'd seen before. Now, notationally, we talked about something called a definite integral last time. Do you remember that? We used that same script S that we've been using for antiderivatives. The number on the bottom and the number on the top told us sort of the end points of the interval we were looking at. And we talked about the fact that if we let our number of rectangles go to infinity, then we could actually find the exact value for that. But that limiting process is a tedious process to do. In fact, as soon as you have more than about 4 rectangles, it becomes kind of nasty. So what we're actually going to take a look at today is called the Fundamental Theorem of Calculus. If f is a continuous function on the interval from a to b, and capital F is any antiderivative of our function, then the definite integral, or the antiderivative from a to b of f of x dx, is capital F of b minus capital F of a. Okay, so what is this actually saying? Well, this is actually saying that if I want to find this definite integral, first I find the antiderivative, capital F of x. Find the antiderivative, same thing that you guys were doing on your quiz on Wednesday. You find that. And then you evaluate it at the top level, the top number, that top limit, in this case b, and you evaluate it at the lower level, the lower limit a, and then you subtract those two values. Okay, so you've got the calculus at the beginning, you've got a little bit of arithmetic at the end, and then you get the exact answer that all of those rectangles were approximating for us before. So we're going to do an example. We have the antiderivative, the integral from from 2 to 5 of negative 3x plus 4. So our first thing to do is to find the antiderivative of negative 3x plus 4. So what is the antiderivative of negative 3x? Good. Negative 3x squared over 2. Is everybody good with that? Plus, what's the antiderivative of 4? 4x. Now, I'm going to show you exactly what I want to see written down. Okay, Evan? So we're going to do this. We're going to write out the antiderivative. You must write out the antiderivative for what I'm going to show you. Must. Then you're going to do a line. No plus c's, and I'll tell you why. In fact, you know what? Let me do a plus c on this one, Evan, and then it'll show you why it doesn't matter. That's actually a good point. Let's do the plus c. We're going to write the upper limit on top, that's a 5, and the lower limit on bottom, that's 2. And what we're actually going to do is we're going to plug the 5 in everywhere we had an x. So this step right here, from here on, I'm going to show you what's going on, and then I'm going to show you a calculator trick to avoid having to write this all out, okay? So what I'm putting this little bracket around right here is not something I necessarily expect to see you write every time. Got it? So, but what we're actually doing is we're plugging in the 5 for the x's. So this is everything with the 5 plugged in. Now we're going to plug in the 2. Okay, that's really, truly what the Fundamental Theorem of Calculus tells us to do. Okay? Now, can somebody tell me, looking at what I've written right here, why I really don't need the plus c's? Yeah, they're going to cancel every time. So when we're doing definite integrals, that is integrals where they have a lower and an upper limit, you don't have to write c out. It's not necessary. All right, for the rest of this, if we simplify this, I'm going to avoid doing all the arithmetic, but you end up getting 19.5, negative 19.5. Okay, and your calculator works just fine to do that value. Okay, or I think that ends up being 39 over 5. Not over 5, over 2. Negative 39 over 2. Okay, try that again. There we go. Is that right? I'm not making that up, am I? Looks okay? All right, you guys ready to see a calculator trick? Well, of course, who isn't? Okay, so if you get to this point, which is where you're supposed to be, what can you do instead? Well, there's a couple things you could do. You could put this equation, the original equation, or the antiderivative you found into your calculator. So let's do it with the antiderivative you found. So go ahead and put in this antiderivative without the plus c. So hit y equals, put in negative 3x squared over 2 plus 4x. Okay, so we're going to put in all of this into y1. Once you get that in y1, go out to the regular screen in your calculator. Not the table, not anything else, just the regular old screen calculator. And then we've used these features before. I want to pull up y vars. So you hit vars, arrow over to y vars. It's a function, and then you get y1. So pluck out the y1. And then you put a parenthesis, and you'll evaluate it at 5. Minus, and then hit vars again. Y vars, function y1. Put a parenthesis, and evaluate it 2, and then hit enter. Did you get it? Did it work out? Did everybody's calculator give them the same answer? Fabulous. Okay, that's one way to do that. Now let's say you're like, okay, great, that's my answer, that's wonderful, but man, I wonder if I did the problem right, because what you're actually using is you're using part of your answer to do that, right? And what if you made a mistake in the part that I highlighted in pink? Right? Then, of course, your numerical answer at the end would also be incorrect, correct? Okay, so hit y equals, and I want you to put in the original equation that you were given now. Okay, so the simplified one that we have here at the top, the negative 3x plus 4. So in y1, I want you to hit negative 3x plus 4, and then go back into the regular screen again. Okay, so the next thing, sorry I don't have my calculator, so I'm going to borrow yours for just a second. The next thing you're going to do is you're going to hit Math 9. And when you hit Math 9, one of two things happens. You either have the newer version of Math 9, because you have a newer version of your calculator, and it looks like this. Okay, so raise of hands. Who has a screen that looks like that? Okay, most of you do. So Hannah, you don't. Marco, you don't have a calculator with you. Who else did not have this view? Okay. All right, I'll talk to those of you who don't have this view in here in a second. I actually think both of them work just fine, but it just looks a little different. It's an older calculator version, usually. Or, what is yours? We might be able to update yours to the newer version if you want it. So, all right, so let me tell you what you put in everywhere. In fact, you can probably tell me. What do you think you put in all these little dotted boxes? All the little numbers that your screen shows, right? You put in, in this case, a 2 down here, a 5 up here. Here you can actually put the y1. I mean, that's why we put it in, was so that you don't have to retype it. And here you put an x for dx. Let me see. She didn't break anything. That's okay, I'll show you how to do it. Cool. Okay. Did everybody who entered this, did it work? Did it work? Did you get negative 19.5? Do you know what that tells you? It tells you that you did the antiderivative right. Because you got the answer from your antiderivative by doing the y1 stuff that we did before, and you got the same answer by doing it the calculator's version of actually doing it before they found the antiderivative. Okay, if you have an older version, you did? Who else did? Just you, Hannah. Fantastic. Okay, so what yours looks like is function integration, so it's still Math 9. F-N-I-N-T, I think is what it says. Your notation is that you first put in y1, you put a comma, you put an x, and you put a comma. You put the lower limit, which is 2, the upper limit's 5, and you're done. It just doesn't have the pretty math face type for it. Who wrote hi on my screen? Sneaky indeed. I'm going to erase it. It will be on YouTube forever. I don't delete any of my videos. Well, not usually. Okay. Are we good? Did it work out, Hannah?
Yeah.
I mean, yeah? Okay. I didn't mean, yeah, okay. So we're good? Everybody's good. All right, cool. All right, so let's do the next one. Next one is a trig function. We have the integral from 0 to pi of 1 plus sine x. So we've got this wonderful feature in our calculator, but it will only give us an approximation when it starts dealing with square roots and things like that. So let's be careful on when we use it and when we don't. So to start with, what's the antiderivative? We're always going to do this step anyway. What's the antiderivative of 1? X, good. And what's the antiderivative of sine of x? Negative cosine of x. And we're going to put that line, we're going to evaluate it at pi and at 0. Now here's the catch. Because pi is being evaluated, that's fine inside of cosine. I'm going to get whole numbers. Great. Fantastic. Not so fine inside of the value x, right? No, it's going to approximate if I do this in my calculator. So I do need to actually write this one out, kind of longhand on this because of the pi. So this is pi minus cosine of pi minus 0 minus cosine of 0. Now we'll confirm our answer with the calculator in a moment, though. We can still do that. Okay, the pi stays as pi. What's the cosine of pi? Either because you remember the unit circle or because you've got a calculator that will allow you to think about it more quickly. It's what? It is -1, actually. Yeah? Cosine of pi is -1. And then what is the, here's a minus and I've got my 0. What is the cosine of 0? 1. So the minus is apart from the minus right here, and then the answer there is 1. Okay, so we're going to simplify. We have, this is pi plus 1, and then what? Plus 1. So this answer is actually pi plus 2. Okay, so, you know, pi is about 3.14, so pi plus 2 would be about 5.14. So let's confirm that our calculator, if I do this with that function integration notation that we just did a minute ago, that it works. So regular screen, I'm sorry, in your graphing screen, you're going to put this in y1. So inside of y1, you're going to type 1 plus sine x. And then you're going to hit back in the regular screen, you're going to hit math 9, and you're going to fill in the appropriate values with 0 and pi. y1 is the function, and then dx on the end. And I think I've said this before, but let me reiterate why in the world you have to care about the dx in the end. The reason is because when you move into further levels of calculus, you won't just have one variable in a problem. Sometimes you'll have more than one, and you have to know which variable you're integrating with respect to, you know, which one you're treating like the variable at which time. So, all right, did you guys get an answer? Is it match what we're expecting about 5.14? Fantastic. Okay, so this is definite integrals. Now, there is another version of the fundamental theorem of calculus. This is my second fundamental theorem of calculus. If f is continuous on a to b, and the antiderivative, capital F of x, is the integral from a to x of f of t dt, then if you take the derivative of the integral, they cancel each other out. Now there's one thing to notice, right? So in essence, what you're seeing is you're seeing all of this go away. And all you're left with is the same thing here, except for what? What's different? X instead of t, right? The variable changed. So that might sort of look to you like, well, that's just some trickery with letters. Nothing really happened. Well, not exactly. Remember, antiderivatives are finding one general antiderivative, right? So it has that plus c stuff on the end, so it's really just like a collection of antiderivatives, you know, shifted up and down. But then taking the derivative afterwards works out not quite the same. So what did you have to say? You're taking the derivative of the antiderivative, yes. Derivative of an antiderivative. It's like saying multiply by 5, then divide by 5, right? Opposite operations. You end up with what you started with. Sort of. So take a look at example 3 and tell me how example 3 looks different than what you saw notationally over here in this actual theorem. What do you see, Caleb? Okay, you don't just see x up here, right? You see sine of x. That's different. X was simply the actual variable x. It's a function of f of x equals x, but it's a very simple function. And not only that, it's a function whose derivative is what? What's the derivative of x? 1. Derivative of sine x, not 1, right? Think about what happens when you take the derivative of something that has a chain rule involved. Do you remember the chain rule? You do the derivative of the outside, and then you have to do the derivative of the inside, right? Okay, well, what we're going to do on this, we're about to do it, is we're going to do this rule. We're going to use this property, this theorem right here, except that we're going to have to do the derivative of that function at the top when we're done. Because there's a function of x up here, not just x up here on top. So it has that sort of extra caveat at the end where I have to take another derivative of the value on top. Okay, so let me show you what happens. When we take this derivative, we're finding f prime of x. It will look just like what we have here with the sign plugged in for t. So this will say sine of x plus 2. But because we're taking the derivative, we have to take the derivative of sine when we're done. What's the derivative of sine? Cosine. And then we multiply this out. So this is sine x cosine x plus 2 cosine of x. The only difference is that we had a chain rule involved. That's really what happened. We had a chain rule involved, so we had to take the derivative of the inside function, the derivative of sine, which is cosine. Mm-hmm.
Why is that?
What we're doing is we're taking the derivative of this, right? Well, we're taking the derivative of something that has an inside function. This is the inside function. So we're going to have the derivative of the inside function. That's where this is coming from over here. While the derivative of the outside of it follows the fundamental theorem of calculus, the second one over here. So the derivative and the antiderivative cancel each other out when you're doing the derivative of the outside function, the derivative of the integration part of it. But just like with the chain rule, the derivative of the inside comes into play. Let's try another one. What do you notice about this one that's different than the last one? Hannah, you're making funny faces at me. What do you notice?
So many changes. 3 minus x.
So there's a 3 minus x involved where the sign was before. What else? There's an x at the bottom. Do you see that? That's actually the biggest difference than the one before. Notice this one before had a constant 0 at the bottom. Notice this one over here had a constant a at the bottom, right? It's a constant. This theorem has a constant in one of the limits of integration and a variable in the other one. So what in the world do we have to do when we have a constant, when we don't have a constant as one of our limits of integration? Well, we're going to apply a theorem that you have seen before. Basically what we're saying is that somewhere along the way there's an x and the other one has a 3 minus x. And I don't even really care what order they're in it. It doesn't make any difference. So I'm just going to put them on there. There are numbers between them. Agreed? Well, sure there are. There's something in between them. And it doesn't even matter if this specific number is in between them, but there's a number. We're going to call it 0. You can call it 10. I don't care what you call it. You can call it a even, as long as you recognize it's a constant. There will be a number between our two limits of integration. So what I'm going to do is I'm going to take this and I'm going to rewrite it. I'm going to go from x to 0 of t squared plus 4. And then I'm going to go from 0 to 3 minus x of t squared plus 4. I'm splitting it up into 2 intervals. Okay? All right, so cool, that's fine. And so this second piece now looks an awful lot like what we did over here. 0 at the bottom, function at the top. I'm going to have to do a chain rule. Okay, fine. But something else is going on over here that's not quite the same. What is it? Yeah, the constant's at the top right now instead of being at the bottom. So how do we change that? Well, there's another rule. We put the negative in front and then we can flip the limits of integration. We encountered that property of integrals last time. All right, everybody good with that? Okay, the good news is that this first function now, aside from the negative in front, looks exactly like the Fundamental Theorem of Calculus, part 2. Right? I mean, it's got the x on top, it's got a constant on bottom. We are good to go. All we have to do over here is to replace the t with x because the derivative of x is 1. There's basically not a chain rule involved because I've got x as my upper limit. The second piece, not quite the same. I need to replace the t with 3 minus x. That's true. So 3 minus x quantity squared plus 4. But then what do I have to do? Yeah, multiply by the derivative of 3 minus x, which is negative 1. I don't know why I've got so many parentheses. That should do it for me. Oh no, I needed that one. Now I know why. It's balancing the one after here. Okay, we're good. We're going to clean that up, of course, right? Of course. All right, so let's see what we have. I have negative x squared minus 4 plus, oh, I'm sorry, it's technically minus. We'll put the minus here. And then I have 9 minus 6x plus x squared plus 4. So negative x squared minus 4 minus, let's see, 9 plus 4 would be 13, so minus 13 plus a 6x and minus an x squared. So I have negative 2x squared plus 6x and minus 17. There's a lot going on in that problem, isn't there? There is. There's quite a lot going on in that problem. All right. Having done that one with the Fundamental Theorem of Calculus Part 2, we will pause for today.